uh, somebody asks for a formula sheet, you really don't get one. You're not going to need, I mean, if there's something complicated, let me be frank about this. Any formulas that I'm going to give you, I'll post. How's that? Any formulas that won't be something assumed, I'll post. So that way, yeah, you guys know me. I mean, my exams, you do the homework and stuff like this, then you're going to do fine. A lot of you, if you don't do it, don't understand it, you're really in trouble. Really that simple. But I know what you mean. When you're asked for a formula sheet, you see, the only formulas I could possibly give you, hold on for 1 second. Hang up. Gone. Hope this works. Bomb. Okay. For instance, with if I asked you something about a waveguide mode, and I wanted an E field, not in the Z direction, all right, say it's a TMO, but in Y or X, then I would give that to you, those formulas, because those are a little complicated, right? If I ask for the impedance of a waveguide, you have to recognize for TE or TM, there's two different types of impedances, and the impedance is always the characteristic impedance of the material that's filling the guide, divided by, if it's TE, if it's a TE mode, it's divided by this 1 over the square root of FC over F squared, right? And if it's TM, then it's times square root of 1 minus FC over F squared. And that FC is for the mode. Does everybody follow me on this? There's a low, that kind of thing for the E fields pattern, I would give that to you. I wouldn't give you the impedance. You got me on this? For the other things like the first, second, and third cutoff frequencies, those are things you have to know. To calculate beta in the guide or phase velocity, those are things you would be expected to know. When we're talking about, I'm not going to give you fiber optic problem. When we have free field equation, right, Helmholtz equation, I expect you to be able to know what the solution is in free space for something that's propagating only one direction. It's a plane wave. Those are things that we talked about. Things like skin depth and all that. You're not really going to need a formula sheet. I'll give you mu naught and epsilon naught, but if you've been doing the problems, that's stuff that's second nature to you by now, I think. So that's sort of my answer. You'll get formulas for anything complicated. Now a lot of that has to do with some applications in EMC and anything that's any kind of equation that, you know how with the, for oblique incidence, I would give you those formulas. I will not give you for normal incidence with the reflection coefficient or transmission coefficient. You know what I'm talking about? With oblique, you're going to have TE or TM modes for oblique. Well, those are a little complicated. I would give them to you. All right? But for normal incidence, I won't. Power, stuff like this, you got to know. All my stuff is based largely on the homework. The way I'm going to make out the test, because it's not made out, I go through the homework, go through the discussions, and I just create stuff. I'll look at, I may pull stuff from old tests, I may not. A lot of times I modify stuff. And how many have had me in here? I see a lot of kids. Just ask them. They can tell you what to expect. And I'll tell you one other thing. When they say your test, I've had kids say something to this effect. Your tests don't look like your Old Testament. Well, that's a danger. All right? Because if you're assuming I'm going to give you an old test, more or less, that's a danger. Don't assume that. They can look quite different. Sometimes they're similar, but sometimes they're quite different. And mine are quite a bit different than Riggs, so be careful. Yeah? I have no idea. I mean, it's all over the place. I just gave a test back. I'm going to give a test back in 3810. Now, that's EEs for non-EEs. All right? I gave two different tests. The average on one was 17 out of 40. On the other was 29 out of 40. Same exact patterns, but it was just for whatever reason, one test statistically seemed to bend one way. I don't know why, and I can't predict that. I can tell you one thing, almost all my tests these days, junior and senior level, are bimodal. I get a lot of people at the very top, almost perfects, and I got a whole bunch at the very bottom that don't know what they're doing. Now, probably in a class like this, your upper level, you'll probably have a lot more better students in here. But in the lower level classes, that's where I see the huge bimodal difference, right? And I get a huge spread. But just ask these guys that have had me, they'll tell you what to expect. Ask him. He likes to talk. All right. I wanted to cover one thing today before we go through the review of the test. All right. And that is really going to be, well, if I can, two. And I mean, first, any homework questions you have? Anything at all? I mean, for beam width, it's pretty straightforward, right? You got an equation, you set it equal to whatever the maximum value of that equation is, you set it equal to 1/2 that value if it's a power, right? Find out what that angle is, and it's symmetric almost always, yeah.
On homework 13, the first one is broken. It says do the following, and that's just a blank square block.
On 13?
Yeah, on homework 13.
I've been having a problem with this. I don't know what happened. I think I pasted over that. I'll check that, all right? I don't have it in front of me, so I can't help you right now. But there are any questions? The homework problems, look, for in the this is maybe what you're getting at. If you're looking, if I'm going to ask for the radiation resistance of something, right? I'll give that to you for the antennas, for short dipole versus arbitrarily long dipole or half-wave dipole. I'll give that to you, all right? Well, the half-wave dipole, you kind of should know, it's 73 ohms plus J, 42.5. But to be fair about it, when I say I cut it down to 0.485, the actual length, then the imaginary part goes away. That's kind of important. The real thing that you're going to be expected to know, for a short dipole, the actual pattern, power pattern is normalized as sine squared of theta, right? The E field I do expect you to know for a short dipole. Y'all hear me on that one? E field for a short dipole, I expect you to know how to calculate that. I will give you for the E field, I'll give you the equation for the arbitrarily long one, all right, and for the half wave. Got it, everyone? And then things like gain and stuff, you'll have to figure out, if I ask you a gain equation, you have to find out what the power is, right, then the normalized power, and then you multiply that by sine theta and integrate the theta d phi to get the solid angle. Then you have to divide that solid angle into 4 pi to get the directivity. And if I assume efficiency is perfect, then it's just gain is directivity. Are you with me, class? All right. I'll get back to this stuff at the last part. I want to cover this one thing. It's going to be dealing with arrays, and this is kind of important. I get this out now, right now. It's not going to be on the exam, but it's important. I do cover this. It should answer a lot of questions. So what we've talked about so far are both loop antennas, short dipole, then long wires antennas, just straight, always center fed. We have not talked about monopole. Matter of fact, I'll tell you what, let me do monopole right now because it's simple to see. What is a monopole? It's based on this. Mono means one. All right, a dipole looks like this, right? And you assume you have a current here, I of Z, and the current below here, I of Z, is an exact mirror image of the current above. Are you with me? Now, when we talk about a lot of practical applications of antennas and how you actually use them, well, you never have this bottom part. The only thing you took is you take a bare wire and stick it up this way, and then you ground the generator and feed only that terminal. Now, the way you get around, the reason we can do it is something called images. So this is charge imaging I have to talk about first. And I don't know if you've had charge imaging before. Now, this is a very important concept because it allows us to solve things without solving bizarre differential equations. And here's why I'm talking about that. If you have a ground right here, that's a 0-volt surface, right? Now, the method of images say this. If I put a charge here, say plus Q, and I wanted to solve for V here, right, at any point, normally I'd have to solve del squared V equals 0, and then I'd have to put a singularity here, and I get a general solution, then I'd have to match the boundary conditions down here. This is, generally speaking, this is going to be a spherical system, and these will be, let's see, the form of the equation for this, I think, are Legendre polynomials. Anyway, what I'm trying to tell you is it's a difficult solution if I have a ground here where this is a perfect conducting surface that's zero potential. It's not something that's spherically symmetric. Follow me? But what the method of images allows us to do is forget about doing that del squared thing, this equation. What we can do is say if this is at a height h and the charge is q, we can move down a height h and simply insert a negative charge. All right, same magnitude, directly below it, a distance h below the ground, just as positive was above the ground h. Are you with me? Then you can say for either the E field or the voltage above here, if you actually saw, you wanted to get, let me try to be real clear about this. Just a rag, no erasers. Well, so be it. If you're out here a distance r1 away, right here, you can say the voltage here is just going to be Q plus over 4 pi epsilon naught R1 plus, remember voltage is scalar, then you would take this distance, which is now R2, only it would be plus, really, or minus Q plus, because that's a minus Q, over 4 pi epsilon naught R2. Now that's a simple scalar equation, and I got it by looking at these things as if they were point charges. And that works for the voltage anywhere above the ground. It doesn't work for the voltage below the ground because it's 0. Are you with me, class? Everybody? Now, that's a trivial solution, right? It's just 2 point charges. And it does meet the boundary conditions. I'll show you. Just take it to any point here. Where R1 is equal to R2, you're at the ground. Are you not, class? Did everybody see that? What's the voltage there? Well, that's Q plus. Factor out Q. It's going to be 1 over 4 pi, Q over 4 pi epsilon naught, quantity 1 over R1 minus 1 over R1, or 0. Follow me? So it meets the boundary conditions exact. And this is a nifty trick. Now, that's for positive charge. Let me show you how this works for current and the way we can figure out what happens if we have current. I always start with charge. When we have currents, what happens is this. Put your ground plane there. That's 0 volts. That's just a symbol for a ground plane. Lossy ground plane's the earth, but it's a ground plane nevertheless. If I have a current in this direction, I want you to notice this current's going to have a current I. It's going to have a centroid of height h, right? Now, when I have current, think about it. Positive charge would accumulate there, and negative charge would accumulate at the base. Do you agree? If you've got current flowing, just think about it, right? Charge is moving. It accumulates positive. There's a reservoir in negative, or takes from the area of the bottom. Do you all understand that? Now just do imaging. Come down here at a distance h. All right. Now I'm going to have that same image thing, but where there's negative charge there, there's positive charge here. Where there's positive charge here, there's negative charge there, right? Now, which way would a current have to flow to create that? You all see it flows this way? Everybody see that? What that tells us is this. We can take anything that's vertical, any current that's vertical, and simply take the image of that current beneath it and literally double the length of a monopole, effectively making it a dipole. So if we have this, which was typically a dipole of length L, I can say that dipole of length L, if it's a monopole, and this is the way a monopole looks, it's grounded there, this is a small distance, and they'll have a plus voltage there, and the other part will be just grounded. They're going to have a current I here. A monopole has a length L over 2. They usually do this. That means the total length of this is L, right? But now this is just an image current. Do you all see this, class? How many see this right here? In other words, effectively the monopole for currents in the vertical direction just extends the monopole to double its length and effectively makes it look like a dipole. Got it? Now here's the trick on this one. This is currents in the same direction. The radiated power for this monopole is only in the upper portion of space. Do you all see this? So there's nothing radiated down here. There's two things that happen. The directivity or the gain double to that of a monopole, and the radiation resistance goes down by half. And that should make logical sense. Radiation resistance is proportional to the power, right? Think about it. If the power is identical in terms of the E field and stuff up here as it would be for a dipole, then the power density out here would be the same. Same radiated power would be in the upper hemisphere. Do you all agree with me? But there's nothing radiated in the lower hemisphere, so exactly 1/2 less power, all right, 50% less. The power is proportional to the radiation resistance. The radiation resistance goes down by a factor of 2, but the gain goes up by a factor of 2 as well. Radiation resistance down, gain up. Does that make sense to everybody? For the same current, that's what I'm getting at, for the same current that's flowing in that thing. All right. Now, that's for currents flowing in the same direction, and this is the monopole. We could go through the gain and stuff like this, but it's not important at that point right now. What about if they're in the same direction? Take a look at this. If I have currents in the same direction, here's a ground plane, and now I'm going to have a current in this direction, I, at a height h. Well, instinctively, you're going to put the charges on here. You're going to say the positive charge accumulates there, and negative charge accumulates there. Follow me? This is the easy way to do it. All right, now I go down a distance h, right? Wherever there's a negative, there becomes a positive, right? Method of images. Wherever there's a positive becomes a negative. Which way is current flowing? This way, right? Current would flow from the negative to, it's forcing that way. It's accumulating positive charge at the tip, right? Where the arrow's pointing and pulling it from where the negative is. Now, what do you notice about these? Currents that way is imaged in the opposite direction. Are you with me, class? And that's true for parallel currents. Perpendicular currents image in the same direction. Does everybody follow me on that? I'm going to see this right here. And you do it with the charge imaging methods, the easiest. You see it, guys? I mean, I want to make sure. Yeah, I'm looking right at you, kind of, sort of. Just follow me on this thought. Positive charge up here, what does it really do? If you would actually look at the ground plane, if you had positive charge right here, I'll just tell you how it looks. I remember doing these problems when I was in grad school. All right, if you looked at the ground plane, the charge density at the ground plane, all right, if that's positive charge, you would gather negative charge here, and the magnitude would look like this. It would be a bell curve. It would be negative charge density right there. This is something we do, right? Now, that negative charge density effectively can be replaced by just a single blob of negative charge right there of magnitude q, only opposite sign, at a distance h down. And it exactly solves the del squared equation. It is the solution without going through the del squared operation, setting boundary conditions equal to 0 there. Matter of fact, anybody wants to do that, see me. I'll be happy to go through it with you. It's an interesting solution. I haven't done it in a while. I said Legendre. I think actually you don't have to use Legendre, but I got to be careful about that. It'd be fun to do. Anyway, so currents in the same direction, or in parallel to the surface, image in opposite directions. Got that, everyone? This is real important when you do any kind of antenna analysis and work. Now, one other thing. What would happen if you had a current like this? So here's my ground, and now I have a current like this, I. Call this H1, this H2. What does that image as? Well, the vertical image vertical, right? The horizontal image horizontal. Do you all agree with me? So what's it going to image like? Well, first I'm going to go down here, H1, and then I'm going to go down here to H2, right? I know it's got, the verticals have to go in the same direction. The vertical component of this is here, so the vertical is going to be going up. What about the horizontal? Opposite. It's going to do this. Can you all see that, class? With me? Verticals same, horizontals opposite. And that would be the method of images applied to an arbitrarily straight wire antenna at a bent angle. Sometimes folded dipoles look like this. Just realize this. That's the only thing I'm showing you. Something to take from this. When I teach EMC, I'm not teaching an EMC this semester. It didn't get enough students. But when I teach electromagnetic compatibility and interference and really the elimination of it, this is big on getting product out the door. It's a huge, huge cost thing. And if you work at the end, what's called compliance, or the last revision before it goes into the field, you're very, very highly paid, because that's what makes money for the company when they sell product. And a lot of times, I got stories about Adtran and Dynetics on this one. Well, really, think about it. More Adtran. When you spend millions and millions and millions of dollars on the design of a prototype, say some kind of a route or something like this, and it's about to go out the door, and it doesn't meet either FCC standards or it gets failures in the field all the time for something that you didn't see, you're left with what's called the compliance guys, and they have to figure out a way to make it work cheaply, all right? Now, that's EMC analysis in a nutshell. And believe me, that is some of the most clever bunch of engineers I've ever seen. They're the highest paid usually in the company, because they're the people that can make the company all the money. They can get product out the door that will actually work in the field. The one product I'm just going to give you this story, and I'll shut up about this stuff, but the one product I'll never forget was Adtran had a chip years ago that was going to be like 100,000 of these chipsets. It's actually not a chip, it's a card. So it's a plug-in card for the cell phone towers. It's going out all over. I suppose Verizon used it. I don't know how many companies used it, right? Lightning was knocking that thing out left and right. They had lightning protection. They couldn't figure out what was going on. So who gets the deal? I mean, Kevin Schneider at that time was the chief technology officer up there. But who gets the deal to fix that thing without starting from scratch, which is billions of dollars probably at that point? All right, well, it's the compliance guys. This guy's name's Jaffe. His son went here, and I knew him because he was from Penn State. He was the head guy there. Now, they got this, get this done in like a month or less, maybe weeks. And you're talking about money that's like your profit for the next year is based on this, maybe next 5 years. So those guys figure out a way to make it work. How they did it, I don't remember everything about it, but I remember it was some very clever compliance engineering where they rerouted things, they prevented any current from getting in the normal pathways, but they had to do it cheaply. That's why these guys make $500,000 and up, all right, as salaries, and that's over. I mean, that's besides bonuses and all that. When you figure out how to save a project like that, they probably get $1 million check in the mail. Those are the highly paid guys. The guys that are in the working with 15, 20 engineers on, you know, another revision of this stuff and things like this, you're going to get your paid your 70, 80, 90,000 a year, all right, which isn't bad. But the ability to jump from that to a 300,000, 400,000 isn't in the normal stream, all right, the way most people go. Some get there. It's going that route, usually compliance or really cutting edge engineering. Does anybody know what I'm talking about here? Does anybody know what compliance is? Those are the guys that make all that money. They make fortunes. And in the military, that's what pays off the charts when you're doing anything that deals with military aircraft and stuff like this. If it isn't working and you fix it, you can write your ticket. Doesn't matter. 300,000 sounds reasonable. Make it 5. Take the next couple of weeks off. All right, that's monopoles. One thing I want to raise. One other thing I always plug, small companies. If you get a chance, after a couple years with maybe a big company or just, you know, getting your feet wet, figuring out what you're really interested in, if you get a chance to work for small companies, that's the place where you can advance and become, if you're into wealth and stuff like this, super wealthy. I have several students that I taught not my last PhD, 3 PhD students ago. His name's Dan Faircloth. He's part owner of Iris, and he's very well off. I remember him when I taught him undergrad in 2006. I think he got his PhD. Let's see, a little over 10 years, and he's worth more than probably this whole department. Hey, think about guys like Tim Cook, right? He's an imaginary engineer, an industrial engineer. Oh God, I'm on tape too. Well, it was nice working here. Now, here's the one thing I am going to do. I just want to show you the one thing about arrays, and then we'll talk about the exam, because you're going to have questions, all right? Now, how many have heard of arrays? What it amounts to is, if one antenna is good, a whole bunch is probably better, and in fact it is. So they're going to assemble these antennas in some orderly fashion to magnify their properties. Actually, it's multiplicative. I'm going to show you how. I'm not holding you responsible for the test on this, but try to appreciate this. Just watch it. You don't have to actually write it down. We'll go through it again. If you have just an antenna right here, E, right? An antenna with a current I. We know that there's going to be an E field out here, right? The way you can think of that antenna creating an E field is you can say the antenna itself, right here, and I'm going to just say this, if I want to know the electric field or the power, better yet, let's do the power density, PAV out here. I can say that the PAV out here, if there's a total power P total going in, that's equal to P total over 4 pi R squared. Now that's isotropically distributed power. Do you all agree with me? It's the same amount of power in every single direction. The only thing the antenna does is focus the power, right? And the way it focuses is with something called the gain. Gain is a function of angle, theta and phi, not of distance r. So gain is something that focuses power in a certain direction. Doesn't increase the amount of power, just focuses that power in certain directions. Got it, class? That's it. When we talk about antennas in general, we can talk about power, or we can say that an antenna itself, actually with a, say, instead of a power, a current, creates an electric field out here, and the electric field is really equal to something, Or you can just take the current times k over 4 pi r squared. Now that would be something, that k there would just be something that would deal with the isotropic value of the electric field from a theoretical isotropic radiator. Think of the sun, all right? There is an electric field from the sun, right? It's not usually thought of that way, but it's at all sorts of frequencies. But nevertheless, you could think of it that way. This is isotropic right there, right? Now, when you take this and you multiply it by the actual square root of the gain, call it the electric field pattern, then you get something where you could put, instead of gain here, you could put in the actual elements, the electric field pattern of theta and phi. So for a dipole, it would be sine theta, right? For like a half-wave dipole, it would be cosine pi over 2 cosine theta over sine theta, right? In other words, that's a function of angle and a function of the length of the antenna, right? Or the shape. Follow me? Now, the way you do array theory is you assume, forget about the individual elemental pattern. You forget about if it's a short dipole, half-wave dipole, a loop. Forget that. You assume everything's an isotropic radiator at first. So you say, I'm going to have a bunch of isotropic radiators. I'm going to just assume these are isotropic radiators. You're going to space them by d. And then we're going to have a total of, say, n minus 1 radiators, and this would be the first one right there. So that's how we count them, 0, 1, 2. Each one of these things is going to have a current I naught, all right? But what I'm going to do is the classic way of doing array theory. The array is along this axis. It doesn't matter if you call it x, y, z. We're assuming isotropic elements. And what you're doing is the first element has just I naught. The second element is going to have I naught e to the j alpha. So it's going to have a phase difference. This is the way you steer a beam classically. The next one is going to have I naught e to the j2 alpha, and so forth. Finally, out here, it's going to be I naught e to the j n minus 1 alpha. Everybody see what's going on here? So it's a progressive phase shift. Now, we're going to go ahead and calculate the E field from all these isotropic radiators at a certain range. Now, just listen to me on this one. The way we do it, we start at this end. If that's x, we're just going to say this is a vector r. And we're going to say r is much, much, much greater than d. So we get no problem with the actual length of the array affecting the E field. We're so far away from it, we don't care. Or a long way away. We're going to say the E field at this range here, I'm going to use Wentworth's way of doing this. He uses this angle, and he calls it phi. There's an angle phi with respect to the line of the array, measured to the radial distance r. Everybody see this, class? Now, the E field out here, remember, it's an isotropic radiators. The E field out here can be thought of as k I naught over, and I can put 4 pi r. I could just absorb this into k. And then it's going to be e to the minus j beta r. That's the first E field from the first one. It's just some scalar k over 4 pi r times I naught. And e to the minus j beta r is the phase change from this point to there. Everybody with me? It falls as 1 over r. Plus the second one. Now that's going to be k I naught over 4 pi r, right? But now it's going to be e to the minus j beta r1. And here I got to do this. Now this distance is r1. They're parallel rays. They're both going virtually to the same point. You're with me? That's the idea. So what's the distance difference? If you look here, the distance difference would be what? Just d cosine of phi. Can you all see that? If this is the angle phi right here, hope you can see it, then d cosine of phi would be here. Everybody with me? Think about it. When phi is 0, the cosine of 0 is 1, then the distance difference is exactly d if you're going that way. And if you're going 90 degrees to it, it's 0, right? They would have no distance difference, right, class, for R1 and R2? So I can say really that R1 is just R, right here, minus d cosine of phi. And then I can write it like this. I'm going to put it up here. I'm not trying to waste time, but what I'm going to do is just say that now I can say that the second term would be k I naught over 4 pi r. Now I'm going to make the case that 1 over r1 is about 1 over r in terms of magnitude. Do you all give me that? 1 over 100 miles is about 1 over 100 miles plus an inch, is what I'm saying. All right, it's about the same, so I'm not going to quibble over that. I'll just leave this as r. Now up here, I have e to the minus j beta, and now there's going to be r, right, minus d cosine of phi. And there's one other thing I didn't say here. There's an ej alpha in there. Correct, class? That's only for the second one. There's a phase change, right? Everybody appreciate what I'm doing here? I'm just going to the second one. We'll extend this to all of them in a second. But if you do that, you all see that I can factor out an e to the minus j beta r there, right? Everybody see that? Think about it. If you multiply, it's e to the a plus b thing. It's e to the a, e to the b, right? So I can factor out e to the, I'm going to do it here. I can say this is going to be e to the minus j beta r, which appears here. And then it's going to be e to the j. Now remember, I'm subtracting that d cosine theta, but there was a minus j beta in front of it. So it would be d cosine theta, or I mean phi, pardon me, plus alpha. You all see what I'm doing? How many do right here? I'm just what? I'm trying to break out the e to the minus j beta r by itself and see what's left. And that's what's left. It's d cosine of phi plus alpha, which is the phase difference between the first current and the second. Now what do you think happens here to the third one? Now that R2. Normally I'd have what? Plus k I naught, right, over 4 pi r, right? Then I would get what? E to the minus j beta quantity r minus 2d cosine theta, right? Because now, look, the distance difference is going to be twice the first one. Do you all see that, class? And the phase change is 2 alpha, right? The reason I said 2 alpha and it's done that way is because now I can factor out e to the minus j beta r here, but then I have e to the j beta, and then it's going to be 2 here, 2 beta d cosine of phi plus alpha. So it's 2 times beta d cosine of phi plus alpha. And this pattern is going to keep on going until I get to the last one. With me? Now I'm going to succinctly write this. I just want you to see how the recursion occurs, right? Every single time I have to add in the additional phase and the additional difference into that minus e to the minus j beta quantity r minus, and then it's going to have whatever the number is I am, d cosine theta, and that's going to be plus the whatever the number is on the antenna times alpha. So succinctly I can write it like this. I can say the total E field at a range would be equal to k I naught magnitude over 4 pi r e to the minus j beta r, and then down here I will have 1 plus e to the j, and here I introduce a symbol called psi, and this is classically done, beta d cosine of phi plus alpha. So it's beta times d. Beta is actual, what, the propagation constant, right? Or I should say the wave number. Beta times d, spacing, times the cosine of that angle, plus alpha. Remember, it's a progressive phase shift. I'm assigning a phase change that's constant. There's a certain amount of phase difference between each one of these currents, and it's continual. When I do that, I call this just psi, plus e to the j 2 psi, plus dot, 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 plus e to the j n minus 1 psi. Can everybody appreciate what I've done there? I've tried to do a shorthand method for establishing what the electric field would be from isotropic sources when they're on an array or aligned on an array with a progressive phase change, same current. Everybody got that? Now remember, I'm doing some things here that you have to realize this is what it's hinged on. The spacing is the same, they're all in a straight line, and the phase difference is progressively the same, right? So that's key. Something else about this, each one of these is radiating the same amount of power, which is a little tough to have happen all the time because the ones closer to the center have a different driving point impedance than these. So you have to have something called a power coupler. Just be aware there's more to this than meets the eye. It's not quite as simple as I'm making it. So now I have this equation, and again, I'll put down psi is beta d cosine of phi plus alpha. All right? Don't worry, I'm going to break it off in a second. When I get this, what do you think this goes down to? Doesn't this look like a series? And really, I could have a series from n equals 0 to n minus 1 of the term e to the what? J n psi. Isn't that right with that, all that exponential stuff, 1 plus e to the j psi plus e to the j. Now that's a very classic one. That's the geometric series, a to the n, where n sum from 0 to n minus 1. I could prove this to you. I'm not going to waste your time. This comes down to be simply 1 minus e to the, and this would be j capital N psi over 1 minus e to the j psi. You remember seeing that probably in signals and systems, right? The a to the n summations, right? Geometric series. I prove that in signals and systems. I'm not going to prove it here. If you want to see it, see me after, not after this class, see me after 2 in my office. Now, after this, anybody know what I'm going to do to make this something understandable? Some of you do, because you've had me. I know some of you know. Well, yeah, sort of, kind of, but there's one trick before Euler's. It's to factor out the e to the j. This is going to be e to the j n psi over 2 upstairs and e to the j psi over 2 downstairs. And what I get now is going to be e to the minus j n psi over 2 minus e to the j n psi over 2 over e to the minus j psi over 2 minus e to the j psi over 2. Follow me on this? Now, if I factor out a minus 1, then you got e to the j n psi over 2 minus e to the minus j n psi over 2. What does that smell of? Anyone? I know you know. What is, what is the sine of theta? It's e to the j theta, right? Minus e to the minus j theta over 2j, right? All right, you realize if you pull out a minus 1, top and bottom, you change the points where these occur, and you just get 2j sine of this argument, n psi over 2 here, and this is going to be 2j sine of psi over 2. So in a nutshell, it comes down to this. You have e to the j n psi over 2 over e to the j psi over 2 times, and then on top, it will be sine of n psi over 2 over sine of psi over 2. I'm just going to tell you that's what this comes down to. Then I can write this whole thing, the E field, from the array. Let me put it here. Then we'll talk about the review. E field from the array itself. Now, Wentworth does it with power. This is the E field. It's just going to be equal to the actual k I naught, that's isotropic, over 4 pi r, right? E to the minus j beta r. And then it's times this. It's the phase form you don't even need to worry about. E to the j n psi over 2, e to the j psi over 2. And then it's going to be the sine of n psi over 2 over the sine of psi over 2. Now, what I can really say is this. This right here, all this stuff looks like the electric field from an isotropic radiator. Forget the phase for now. We don't care about it. Here is the multiplicative effect of the array. Now, does anybody know what this actually, what the maximum value of that is? Some of you do. Well, it's sine of n psi over 2. If you took a, think about it, at 0, isn't this indeterminate? You have, if psi is 0, it's indeterminate, right? All right, well, then you take derivative top and bottom, right? You're going to see you're going to get an n over 2 and a 1 over 2, or 1/2 n. The effect of the array is the electric field is magnified at its maximum value by a factor of n, the number of elements. Got that? That should make sense to you, right? Each element has an electric field of a certain magnitude. If you got all of them in phase, you should get n times that field. In effect, you do. It's a one-dimensional array, so you're going to have n times the electric field of one of the maximum electric field of one of these. But the power goes up by a factor of 2. That's n squared times e. The power density, I should say, will go up by a factor n squared, which is important. That means the arrays themselves magnify the peak power density by n squared. Yes, sir?
So does the geometry of the array affect it at all?
You mean the orientation of the elements. Each individual element does, and here's why. What we're going to see this, and this comes up next, is the total electric field from an antenna, from an array, is the electric field from the pattern from the individual elements, right? Times the electric field pattern caused by that. So you multiply the two. In other words, what you're getting at is, suppose say I've only had 3 elements. If they're dipoles like this, right? In this direction, I'll have no power. You notice that the dipoles themselves radiate 0 power up and down the axis they're on, right? This array doesn't help that any. Right? There's still 0 power. The maximum power will be in this direction, perpendicular to the antenna element's orientation. That's important. Now, if they were oriented like this at 45 degrees, the maximum power still would be in the 45-degree angle, but there would be but to get that, you have to change the phase progressively, and that's later on. We'll talk about that. It's always with the orientation of the maximum power from one element. That will be the direction of the array's maximum power. The amplification possibilities can be a maximum in that direction. Comes later. Now about the quiz, or about the test. What the test, you're going to ask me how many problems. 4 problems, multi-parts. If anybody knows me, ask the people that have me. You're going to get four problems. They'll have multiple questions asked about it. You're going to get a waveguide problem. You're going to get propagation. So you get chapter 6, right? You got chapter 7. You're going to have waveguide. You're not going to get fiber optic. You're going to get propagating wave problems. You're going to get reflections too, right? Because propagating waves into a media where you got 2 different medias. You're probably going to be asked things like the power density, how much power is reflected, how much power is transmitted. Possibly something about Snell's law, which you will be expected to know. Like if an angle is a certain angle coming into a surface and it's water, what's the angle bent downward, all right? Anything with reflection and transmission coefficients that is oblique, I'll give you. If I want you to know, if I'm asking something like that, I'll give you the formulas. When I talk about waveguides too, I'm going to just throw this out there. Remember, I gave you one classic problem where a waveguide, when we had a waveguide, we viewed it as a transmission line. Do you all remember this? And we had to calculate the input impedance to the waveguide in the amount of power delivered to a load. And we viewed that just like we did the transmission line problems. Only we changed the beta in the guide. Do you all remember that? And we changed the characteristic impedance. No longer is it just Z0, it's the characteristic impedance at that frequency for the mode. Does everybody recall that? So that's the important thing to gather out of that. Waveguides, that could be a part of that waveguide problem. You have to know the phase velocity, group velocity, wavelength in the guide, beta in the guide. These are all things you had homework problems on. Now, with propagation in general in free space, 1D only, all right? Only one-dimensional propagation, Z direction or something like that. Not multi-directions, right? Just one direction, and it's going to be in the standard format. I'll use X for the vertical for the E field probably, or something like that. And it will be in the Z direction propagation. I'm not going to try to throw you a terrible curve. For antennas, short dipole, loop antennas. Short dipole, I want you to know the field for, E field and H field. For loop, I'd give it to you, all right? For arbitrarily long antennas and even half wave, I'll give you a field equation, all right? The electric field equation. Now, you'll be expected to know how to get gain, directivity, beam width, things of that nature, all right? And since I haven't made up the test, I can only tell you, I'm not going to do you slab waveguide, don't worry about that. The reason I'm not going to is because there's nothing here to test on. I mean, if you look at the equations, There's really not. They don't show the characteristic input impedance to a slab waveguide. They don't. Polarization is another something. Skin depth. Remember how to get AC resistance versus DC. We talked about that too because of the skin depth. Going through this, making sure I'm not forgetting anything.
Did you say not polarization?
No polarization of a wave. Circular. All right. I mean, that could be, yeah. Power, let's see. Yeah, reflection, transmission. Waveguides, the impedances, how many modes. That's a lot like the actual quiz you got. Things like for the antenna section, total radiated power, radiation resistance, directivity, gain. Those are all fair topics. You're not going to get anything on arrays or monopoles on this test. So you got a fairly limited amount of material compared to like what will be on the final. But you have to understand something. The biggest problems right here usually come when there's confusion about the basics, like the mode of operation. Things like that, people mess that up. Remember, there's always that factor of 1 minus FC over F squared for waveguides. And that FC is going to be the cutoff frequency of the mode you're talking about. For instance, the 1.0 mode's the lowest order mode that allows propagation. You have to be above that for propagation. Other than that, I'll answer any questions. There's no formula sheet except I would give you the formulas for oblique. All right, and yeah. What's that? Say it again. You want a half angle identity?
2 homeworks ago, they were like needing half angle identities to calculate the angle.
What? What's that?
I assume you're going to make Emag questions, not trig questions.
Well, I'm trying to think of it. I remember this cropping up, but what was it for? Wasn't that, no, you know what that was for? That was for, actually, for optical transmission, when we did the thing where we had numerical aperture of a fiber optic. Remember, numerical aperture, we have to take we had to come in at a certain angle, then it bends, then it hits, and that angle it hits between the cladding and the fiber has to be the critical angle, right? For total, that was where we got that half angle thing from. I'm not testing you on that. I can. We want optics. No. I would not. I put everything in the time domain. If I give you anything with right-hand circle, here you go. You drop this. Right-hand circle, isn't that yours? Something came, it fell right there. Maybe it's mine. Just like anything like that, you would actually.